In this lecture, we're going to be talking about the stack-based buffer overflow. This will be the first in a series of lectures that we give about modern vulnerability exploitation. So we'll begin with some history. The idea of a buffer overflow as a potential security vulnerability is understood as far back as 1972, potentially earlier. And we see it mentioned in this planning study that was called the Computer Security Technology Planning Study, which you can Google for actually and read if you're interested. But it wasn't until 1988 where stack-based buffer overflows really came into the public spotlight with the Morris worm. So the Morris worm was written by a Cornell student, Robert Morris, and according to him, he didn't have any malicious intentions, but he was really trying to gauge the size of the internet. But the way the worm was written, it was possible for the worm to reinfect machines that already had been infected, and this essentially had the effect as having a large-scale denial of service attack. And so this one in part targeted the Unix's finger service. And for more details, you can go online and read. There's a whole history about this particular worm. But this actually led to the first criminal conviction under the 1986 Computer Fraud and Abuse Act as well. Fast forward to 1996, and we had a paper called Smashing the Stack for Fun and Profit that was published in the Frack magazine. And this is a great paper to go back and read, sort of introducing the concept of stack overflows and how it all works. So if we take a look at a few examples here of where stack overflows have been used in practice, in 2001 we had Code Red. This occurred in July and targeted IIS servers. And just in one day, 359,000 computers were hit. Interestingly, this particular vulnerability had been, a patch had been released, I believe about a month before the main attack hit, but because a lot of people hadn't upgraded, it spread like wildfire. Another popular example is the SQL Slammer worm. This occurred back in 2003. Again, small size, targeted another Microsoft product. This was SQL Server 2000. And also in this case, a patch had been released 6 months beforehand. But in just a mere 10 minutes, 90% of all the machines that were vulnerable had been affected. And another example, this one's slightly different because it didn't act like a worm in the other two cases. This was known as the Twilight hack and was an exploit on the Wii console. And the way this one worked is that in the Zelda game, in the save file, you could have a much longer name than expected by the game for the Zelda's horse, Epona. And so what you could do is you could have code that you wanted to run as a program on an SD card, and then basically when the horse's name was brought up in conversation, you could get it to load whatever module that you wanted to run. So as far as a percentage of total vulnerabilities, you can see here on this chart, this just goes up to 2009, so it needs to be updated. But you can see the wide growth in terms of the percentage of total vulnerabilities where stack-based buffer overflows have been used. And this data was gathered from the National Vulnerability Database. So it's definitely quite common, but a lot of new security technologies have come out which have made exploiting these types of bugs much more difficult. There's also a lot better software now, static analysis type products out there that help identify known functions that are vulnerable or unsafe to use, and a lot of people are better educated now in terms of the how to avoid stack overflows in their products. But nonetheless, you still find them, and it's a very common vulnerability. So the next few slides, we're going to go through some terminologies so we're all speaking the same language. First is to delineate between a stack overflow and a stack buffer overflow. The stack overflow actually is just when the size of the stack is insufficient, and this actually isn't an exploit but an out-of-memory exception. When we say stack overflow, especially in this lecture, and when most people talk about stack overflows, they're really talking about stack buffer overflows. You may also hear this referred to as a stack overrun or stack smashing, but it's all pointing back to a stack-based buffer overflow. As far as the term buffer, here we're just talking about a contiguous section of limited memory. So in C buffers commonly exist as just arrays, and strings in C are just null-terminated char arrays. And so the code here is just an example of a string, a hello string. You can see it's just declared as a C string, a char. When we talk about bounds checking, in C and C++, there actually aren't any bounds checking. And so this is what makes it possible to index values outside of an array. And this can lead to memory corruption and exploitation. So this is an example here. We have a very simple program that's just printing out indexes 0 through 3, but note that the array itself, the N array, is defined to just have 3 elements. And so on the very last, when we print out index 3, on the right, when the program has been run, you see that we print out 1, 2, 3, and then there's an address. Well, that address this is printing an item on the stack beyond the array. So the buffer overflow, this is just simply when we say buffer overflow, we're just referring to the writing of data past a buffer's boundary. And so in this code example here, this is a buffer overflow. This isn't an exploit. This is just simply a for loop that the programmer, in this case, this has a simple error where he's iterating from 0 to I is less than or equal to 3. Well, the N array is allocated to just have 3 elements, and so this is going to overwrite beyond the bounds of N the integer constant FF. So when we specifically are talking about stack overflows, this is a subset of possible buffer overflows, right? Because you can have variables allocated in a heap and have heap overflows, which we'll have a whole separate lecture to talk about heap overflows specifically. But on a stack overflow, this is a buffer overflow of a variable that's on the stack. And so if we look at this notional diagram here, one thing that's important to understand is the direction that the stack grows versus the direction in which overflows happen. So the stack grows from high addresses to low addresses. In this diagram, we have the stack growth pointing up, but you'll note that we have the high address at the bottom. And so at the high address, you have the return address, save base pointer, you have local variables, and then there's some variable that you're overflowing. When you overflow, the overflow is happening in this diagram down, so you're overflowing down towards the return address. In the actual address, though, this is going from low to high. So C strings are just, as we mentioned before, these are just arrays of characters. The arrays are terminated with the null byte at the end, and so a major source of overflows occur when dealing with C strings. And so this code here just gives an example of a simple buffer overflow. Again, this isn't going to trigger exploitation in this case, but here we have 2 C strings, the source and the destination. The source is, we have 7 bytes allocated, whereas the des, we just have 3. And the stir copy operation here, you're copying a larger buffer into a smaller buffer, and so this is going to trigger a buffer overflow. So let's walk through an example now in a little bit more detail. So in this example code here, we have a C string defined, a 16-byte C string, and we're calling the gets function, which the gets function just simply takes input until the user new line character is entered, and then this is going to print it out. So gets is one of the worst functions as far as, because there's absolutely no bounds checking. It doesn't check to see is the buffer where the data is being written, is it match the size of the input. It just simply writes it out. So this is an extremely dangerous function that should never actually be used. But in a lot of older programs, this was actually quite common. All right, so here we have, in this first case, this is just a 16-byte input. So we've run the program, we've typed in ABCD, etc. up to O, so 16 characters. The top part of this diagram in Ollie just shows our call, where we're taking calling the gets function, and then in the bottom we take a look at the stack, and here we can see where the data has been stored. So you have at the very top, this is a pointer to the format string, %s. Next, then you have a pointer to the actual input string that the user typed in, and then you see the next 16 bytes contain all the characters that were typed in. So recall that Intel's in Little Endian, so the A is actually at the right, so 41, 42, 43, 44, etc., all the way up to 4F were entered. So in this case, nothing was overflowed because we entered, this was all within the space that was allocated on the stack. So now let's take a look at what happens when we input more characters and we actually do overflow the stack. So now we've entered 0 through 9, 0 through 5, and then A, B, C, D, E, F, G. So on the left was the first input we saw before, and now if we look on the right, you see a pointer. You have the pointer to the string that was entered, and then now we've completely overwritten the return address. So previously we had, so right above the return address on the left side of the diagram, that's the pointer to the saved base pointer, frame pointer, and then right below you have the return address. Here, the string that we input, you can see that that was completely overwrote that. So we've overwritten both the base pointer as well as the return address in this case. So what's actually going to happen when this happens? Well, it's still going to print correctly. Then the program's going to restore a bad base pointer, which is an error. It's not critical error, so that's not going to immediately crash the program. But then when it gets down to this 474645 address, that's a bad address, and that is a critical error, and that's going to trigger an access violation. And so you see at the very bottom here the message that you'll see, which is access violation when executing then that address. So one of the things that comes into play when we're talking about stack overflows is the difference between highland and lowland addresses. So in Highland address, the most significant byte in the address is 00. The nice thing about is not 00. The nice thing about Highland addresses is that this gives us an unlimited injected code size, and we'll see why in the next few slides why that is. On Linux, the Linux stacks are in Highland address space, so that's nice from an exploitation standpoint. Lowland addresses, on the other hand, the most significant byte in the address is 00. And so this is actually has the effect of limiting our injected code size. And you'll see that Windows stacks are in lowland address range. So to understand a little bit more about why that affects how much we can inject, it comes down to Endianness. So on x86, this is a Little Endian byte ordering. And so if we look at the diagram at the bottom, suppose that the data value that you wanted to, that's in the register is ABCD. Well, the way it's actually going to be stored in memory is the D, which is the least significant byte, is stored first, followed by C, B, A. So basically in reverse order. And so because of this, low-lying addresses can really only be injected into your shellcode when they're the actual last item. This is specifically the case when you're dealing with strings, string-based attacks, because the string operations will continue until they encounter a null character. And so this will become clear here in a little bit. So in a Stack Overflow, sometimes you may only actually need a partial overwrite. And there's going to be cases where only a partial overwrite, that's the only opportunity that you do have. And this is the case with a lot of off by one errors, which are very common, similar to the code example we saw previously, where we were iterating through an array, and instead of having less than the upper bound, there was a less than or equal to. So that's a classic example of an off by one error. So just to kind of illustrate this with the indiness, suppose we are going to overwrite 4 out of 4 bytes that we have in our overwrite with A's. So the ASCII code for A is hex 41. And so in this case at the bottom, you see, so at the top, this is what the stack should look like. You can see the save base pointer, return address, and then there's this 6C value. We override them with all A's, and then there's followed by null byte. You see 41414141, and then the 6C has also been overwritten by the null terminator. We do 3 out of 4 bytes. We have the 414141, and then the null terminator. In this case, the 6C is not affected. 2 out of 4 is going to look like this. 1 out of 4. Now you actually see the 40 in the original return address is now there, but we've changed the low 2 bytes. And if we don't put any A's and just have the null, then we've overwritten that partial overwrite. So that just kind of gives you an idea of if you are depending if you only have a partial overwrite, you may be able to get a pointer to some other area in code that is valid, and so you may not need to actually completely overwrite the return address with something different, depending on the situation. So moving on to talk about some of the common exploit vectors that you do run into. A lot of these are all C functions. So gets we've already talked about. This is the absolute worst. Very unsafe. Never use this one. Because this function, again, just simply takes whatever the input is, writes it into the buffer that's passed. And so you're pretty much guaranteed to have an overflow if that function's ever used. Then there's the whole scanf family of functions. And if, in this case, with scanf, if there's no precision specifiers, that means there's no bounds checking, and you also have vulnerability at that point to an overflow. In C++, if you use the cn operator to a char array, again, there's no bounds checking. So in this case, if you are using cn, you should be using the .get or get line with length specifiers. And then there's a whole slew of unsafe string functions. So this isn't a complete taxonomy of all unsafe functions, but to give all the string functions that don't have length specifiers are bad. But there are length specifier alternatives like str copy and str cap. But even these functions are risky because they're very notorious for off by one errors. Just like in loop, where there's a less than or equal to. It's also very common that when using these, the wrong value will get used for the length, and that then opens the door to potential exploitation. All right, so suppose you found a weakness, you found a potential stack overflow. What's your target? What are you trying to do with this? Well, there's sort of two main ones. Is that you're trying to control pointers, or you're wanting to manipulate local data, right? And so some of the pointers that you can target, one of the most common ones is the return address. If you recall from the diagram we saw previously, if you overwrite one of the local variables, for example, and then you can use that to overwrite the return address, then it can return to your shell code, and you gain execution that way. Another target might be structured exception handlers, and we'll talk in more detail about this later in the lecture. VTable pointers, another target, and just function pointers in general. So if you remember from a few lectures back in the reverse engineering lecture when we talked about how C++ virtual functions, how those were allocated, how the VTables were created, and you essentially have all these different pointers. Well, as you can imagine, if you were to override any of those, when those functions are called, that's going to then trigger your code. And so any function pointer that you can overwrite, when that function is called, or however that function pointer is used, that's when you're actually going to gain your execution at that point. With local data, it's a little different from controlling pointers. Here you're trying to change the value of critical variables. So imagine you have a program that has a local variable defined that indicates value of 1 if you are an authenticated user, or a value 0 if you're not authenticated. And suppose you just have a simple 1-byte overwrite. Well, if you can just overwrite that 1 byte from 0 to 1, then you can suddenly make yourself an authenticated user. Another example might be if the application is doing something with pricing. If you can do an overwrite that affects the overall price that's calculated, then that's, you may be able to cheat out of money. So there's many different things depending on where the variables are, where they're located, and what you have control of, where you may be able to influence program behavior by overriding particular local data values. So to drill down a little deeper, we'll start by talking about how you actually would exploit something like the return address. So this is a similar diagram we had earlier where we showed the direction of stack growth versus the direction of overflow. And in red here is what the attacker is going to be trying to overwrite. So basically at the top here we have the overflow variable, and then everything is overwritten down to the return address. And so once in the return address is going to be pointing to the beginning of your shell code. And so essentially once that function exits, then that's when you're going to gain execution, because it's going to hit that return address, and then it's going to go to your shell code. And that's when you gain control at that point. All right, so let's walk through an example. Here again we have this function where we're using gets. And you can see this is the good entry where we just entered A through O. Now let's compare that with an exploit entry. So on the right here we have just some very basic Python code that's building up some shell code. This shell code actually isn't doing anything in particular. We have what's called a NOP sled or no-op sled. NOP sled is just a bunch of no-op instructions. So the opcode for no-op, recall, is hex 90. And so NOP sleds are typically used if you don't know exactly where you're going to land. You might have a large section of NOP, so as long as you can get execution to jump somewhere into that your NOP sled, then it'll just be a series of no-ops until it gets to your actual shell code. That's a common technique that's used, is to create these NOP sleds. In this case, we're not actually going to have anything for the shell code, so you see that's just blank. And then we have 4 padding bytes where we're just repeating the A character. And then our egg, which is just what we're calling our shell code that we're going to pass, is just the concatenation of the NOP sled shell code padding. And then at the end we have the pointer. This is what's going to overwrite the return address, because remember we want the return address to point to the beginning of our shell code. And so if we look at the stack here, the beginning of our shell code is going to be at address 12FF70. And so that's why we put that at the end, because that's where we want to have our return. Um, and then the rest of the code just basically is to run the executable and then send it the egg. And so on the right here we have, you can see the code. So once you've done Airflow, you see this 16 no ops. There was no shellcode, so the next thing you should see is the padding. So you see the 4 A bytes. That's the 41414141. And then at the very end there, you see the pointer back to the beginning of the shellcode. So that's that. And this just shows the exploit from an Ollie debug. And so in this case, again, nothing particular is done. This just shows how the exploit would actually work. And a few points that are worth noting is that in a lot of modern programs, there's all sorts of protections that are implemented, which we haven't really gotten into much detail about here, but there are non-executable stacks. So just simply overriding this may not be enough, right? There's also something called address space layout randomization, and we'll talk more about that in other lectures. And so there's a number of things that make this process more complicated, but just in this lecture, we're trying to give you the basic concepts of how a Stack Overflow works. And so the assumption here is that the program's going to be loaded at the same address, and that we can execute code off of the stack. All right, so that's how you would exploit from the return address. The next part that we're going to talk in more detail about is how you would exploit the structured exception handlers. So in the previous lectures, I've mentioned structured exception handling, but not in much detail about how it actually works. So SEH works simply by, when an exception occurs, the SEH chain is traveled. So the chain this is a linked list of handlers. And so each handler can either handle the exception, or it can just pass it on and it will go into the next handler in the chain. If it turns out that there is no handler, it's called, then the default unhandled exception filter is going to deal with it, and you'll get a box like this pop up under Windows where it says it's encountered some problem, it needs to close, and this gives you the option of being able to debug the program. And so if we look at how the handlers are set up, this is essentially a linked list of handlers, and this just shows at a high level. For one record, we have a pointer pointing to the next record, and then there's also a pointer to the actual handler routine. And so in this example, we have one of the handlers. The first one will handle divide by zero errors. The next one handles excessive string lengths. The next one handles missing files, etc. And so each of these, it's very simple. You just have a linked list to the next record, and then a pointer to the handler. And the last handler in the chain, notice that the next record is going to be, all Fs, which is -1. And so that's how it knows that it's at the end of the handling chain. So in C, you can set up these using just try except blocks. What this essentially does is it creates a guarded block. So everything in this try block is going to, any exception in here is going to then go through, and it's going to call this exception handler, which in this case, the exception handler just simply prints exceptions. So this is very basic, but this is how you would set it up in your code. So when the compiler generates the code, it's actually, it, quote, registers each handler. So an exception registration record, there's two parts, right? There's the pointer to the next structure exception handler, and there's a pointer to the handler, which is essentially a function pointer. And so if you look at the two diagrams here at the bottom of the screen, you can see it's you have a pointer to the next SEH and then a pointer to the handler. And you can then see those on the stack. And again, there's the default structure and exception handler. This is going to be towards the bottom of the stack. And then you'll also see here the its FFF value, which is the indicating that's the end of the SCH chain. And then you see the SC handler address, the 7C839AD8. All right, so that's how it works. Now, how do you exploit it? Well, there's sort of three main parts to this. The first part is that we want to overwrite the next SCH pointer. We want to overwrite the SC handler. That's the function pointer, and we want to create an access violation that's going to be handled by the SCH chain. So, for the first part, we're going to, and on the next few slides, these will all become clear about why we're doing what we're doing. But the first value we overwrite is going to be a short jump, jump to 6 bytes forward. So this is going to essentially be jumping over our SE handler pointer. The SE handler pointer, we want to have it point to somewhere in, say, NTDLL, but it could be any pop ret instruction. Again, we'll explain why you want it to point to a pop ret instruction sequence. To find that, you can use in the Metasploit tool, which we talked about in one of the previous lectures, the MSF PE scan. That's a useful tool for actually finding these sequences in DLLs and other routines. So we use that tool. And for the last part, we just simply need to have some overwrite that's going to create an exception. So let's explore this in a little bit more detail. So first, why the pop ret instruction sequence? Well, the exception disposition struct gets placed on an independent exception dispatcher stat, right? And then the establisher frame, this is what's pointing to our SEH registration, which is one of the values that we've overwritten. And this is located at ESP plus 8 on the new stack, right? And so when our handler gets executed, which is what's, when the exception's triggered, it's going to hit our handler. This is going to be pointing to somewhere in a DLL or some piece of code that has that pop ret sequence. And then because of that, if we go back up, ESP plus 8, well, if you have 2 pops, that means the stack pointer is now pointing to the frame, the establisher frame. And then the ret instruction, ret, if you recall what it does, is that it's going to take value off the stack, and execution is going to go to that address. So pop ret will begin execution at our SEH registration. And then recall that we had the jump that was overwritten with the jump plus 6, which will take us to our shellcode. So to illustrate this in a little bit more detail, visually, again, we have the first entry, you have locals, you have the next SEH pointer, that's, remember our linked list struct that we talked about before, and then you have the function pointer to our actual handler, our exception handler, okay? And so for the SE handler, that's the function that's going to call when the exception's triggered. That's where we're going to have pointing to someplace in code that has a pop ret address, right? That sequence is going to then in turn cause execution to continue to the next SEH address, which we've also overwritten. In this case, we've overwritten with it a jump plus 6. Well, the jump plus 6 will jump over that address, the pop ret, and into our shellcode. So we have an overflow, we write in the jump plus 6, we write in the pointer to the pop ret address, and then we have our shellcode. And so one question you may be wondering is like, well, why not just make the pop ret point to the shellcode? Well, the reason why is because we can have this point to a Highland address in something like NTDLL, for example, which gives us more room, much more room to place our shellcode. And so this shows in a little bit more precise details the normal stack frame versus the overflowed frame. So again, we see sort of on the right-hand side, the first step is the address to the pop-pop-ret function, comes back, returns to stage 1, which is the short jump to stage 2, and then executes the payload. So if you want to explore SEH exploitation in more detail, there are a lot of papers and tutorials on the internet that describe this in a little bit more detail, but that's the basic concept. And again, as with the things like non-executable stack protections, there are, to defend against SEH exploitation, there's something called safe SEH. Safe SEH, there's checks to make sure that the address of the handler is within a particular table, that the table gets compiled into the program at runtime. So that basically, what that's doing is it's making sure that the handler is pointing to some place in your program that's been registered at compile time. And so that's one of the defenses that are out to make this type of exploitation more difficult. So to show this, an example of what this would actually look like in practice, here we have all the 4141 bytes that you see. That's from our overflow. Those are just the A bytes. Then we get down to the pointer to the next SEH record, and then there you can see we have 2 no-ops followed by the 06EB. That's the short jump plus 6 bytes forward. And then we have a pointer to the SE handler. That's where this is pointing to somewhere in NTDLL with the pop-pop-ret. Now this particular address, it's worth noting, is actually in a safe SEH module, so this particular exploit wouldn't actually work in practice, but it just is for illustrative purposes here. And then beyond that, we have, you can see all the shell code that would get executed after. So basically, it's going to first go to the 7C87F422 address, which is pop-pop-ret. Then it's going to go to it's going to return to 12FF70 on the stack, which we have the 2 no-ops and then a short jump, and then that's going to take us into the shell code, and then you've gained execution at that point. And then, of course, to trigger this, you need to actually trigger some sort of exception or access violation that's going to make your handler be called in the first place. And that's it. So that wraps up this module. Again, like I mentioned before, there's some great references out there if you're interested in stack-based overflows and would like to dive into more details. There's a lot of great references. The 1996 paper about smashing the stack for fun and profit, great reference to look up. And there's plenty of papers that talk about stack overflows in modern times when you're dealing with a number of these newer defenses that are out that make stack-based buffer overflows more difficult. So, as always, if you have any questions or follow-up, send us an email, and that concludes this lecture. Thank you.